CT scans of Earth links deep mantle plumes with volcanic hotspots and island chains. This is by California University, Berkeley. Seismologists there produced for the first time a sharp three-dimensional scan of Earth's interior that conclusively connects plumes of hot rock rising through the mantle with surface hotspots that generate volcanic island chains like Hawaii, Samoa, Iceland. We have the hotspot in La Palma volcano that's going off now, the Canary Islands, and we recently learned that was a super-eruption site 700,000 years ago, between the last super-eruption of Yellowstone 630,000 years ago and the Long Valley Caldera supervolcano in California 760,000 years ago. Yes, the Canary Islands are a hotspot, and they had a super-eruption of 700,000 years ago, and that's a surprise because we didn't know it until recently. Now, essentially, a computed tomography or CT scan of Earth's interior. The picture emerged from a supercomputer simulation at the Department of Energy's National Energy Research Scientific Computation Center, NERSC, at the Lawrence Berkeley National Laboratory. While medical CTs employ X-rays to probe the body, the scientists mapped mantle plumes by analyzing the paths of seismic waves bouncing around Earth's interior after 273 strong earthquakes that shook the globe in over the past 20 years. Previous attempts to image mantle plumes have detected pockets of hot rock rising in areas where plumes have been proposed, but it was unclear whether they were connected to volcanic hotspots at the surface or the roots of the plumes at the core mantle boundary 1,800 miles below the surface of our Earth. The new high-resolution map of the mantle, the hot rock below Earth's crust but above the planet's iron core, not only shows these connections for many hotspots on the planet, but reveals that below about 1,000 kilometers, the plumes are between 600 and 1,000 kilometers across, up to 5 times wider than geophysicists thought. The plumes are likely at least 400 degrees Celsius hotter than the surrounding rocks. Finally, support my Patreon account. The daily posts are 5 videos daily, and they are totally different from what I have on my YouTube channel. Thank you so much for your support and that you find all my content so interesting. You'll find the Patreon account details in the description box. No one has seen before these stark columnar objects that are contiguous all the way from the bottom of the mantle to the upper part of the mantle. This is what first author Scott French, computational scientist at NERSC, who recently received his PhD from UC Berkeley, said. Senior author Barbara Romanowicz and UC Berkeley professor of Earth and Planetary Science noted that the connections between the lower mantle plumes and the volcanic hotspots are not direct because the tops of the plumes spread out like the delta of a river as they merge with the less viscous upper mantle rock. She said these columns are clearly separated in the lower mantle and they go all the way up to about 1,000 kilometers below the surface, but then they start to thin out in the upper part of the mantle, and they meander and they deflect, she said. So while the tops of the plumes are associated with hotspot activity, hotspot volcanoes, they are not always vertically under them. The new picture also shows that the bases of these plumes are anchored at the core mantle boundary in 2 huge blobs of hot rock, each about 5,000 kilometers in diameter, that are likely denser than surrounding rock. Romanowicz estimates that those 2 anchors directly opposite one another under Africa and the Pacific Ocean, for example, have been in the same spots for 250 million years. French and Romanowicz, who also is affiliated with the Institut de Physique du Globe and the Collège de France in Paris, will publish their findings in the journal Nature. The Earth is layered like an onion, they explain. The exterior crust contains the oceans and continents, while under the crust lies a thick mantle of hot but solid rock, 2,900 kilometers thick. Below the mantle is the outer core, composed of liquid molten iron and nickel, which envelops the inner core of solid iron at the center of the planet. Heated by the hot core, the rock in the mantle rises and falls like water, generally simmering in a pan, though this convection occurs much more slowly. Seismologists proposed some 30 years ago that stationary plumes of hot rock in the mantle occasionally punched through the crust to produce volcanoes, which is the crust moved, generated island chains such as the Galapagos, Cape Verde, and also the Canary Islands, where we have La Palma erupting now. Now, the Hawaiian Islands, for example, consist of 5 million-year-old Kauai and to the west, but increasingly younger islands to the east because the Pacific plate is moving westward. The newest eruption, Loihi, the seamount, is still growing underwater east of the youngest island of the chain, the Hawaii, the Big Island. But until now, evidence for the plume and hotspot theory had been circumstantial, and some seismologists argue instead that hotspots are very shallow pools of hot rock feeding magma chambers under volcanoes. Romanowitz, who uses seismic waves to study Earth's interior, had previously worked with French, then a graduate student on the tomographic model of the upper 800 kilometers of the mantle, which showed periodic hot and cold regions of rock underlying hotspot volcanoes. The new study completes that picture down to the core mantle boundary. She noted that if higher temperatures alone were responsible for the rising plumes, they would be only 100 to 2 kilometers wide, ballooning out only when they approach the surface. The fact that they appear to be 5 times wider in the lower mantle suggests that they also differ chemically from the surrounding cooler rock. This supports models where the material in the plume is a mixture of normal mantle rock and primordial rock from the dense rock anchoring the plume at the core mantle boundary. In fact, lava emerging from hotspot volcanoes is known to differ chemically and isotopically from lava from other volcanoes, such as those erupting at subduction zones, where Earth's crust dives into the upper mantle. As the supercomputer analysis did not detect plumes under all hotspot volcanoes, such as those in Yellowstone National Park, the plume that fed them may be too thin to be detected, given the computational limits of the global modeling technique, French said. But we know the mantle plume is coming from Baja, and it spreads out like a delta, and it's a Y-shaped. The western part goes under San Andreas Fault and the Walker Lane Fault system, where we have the very high threat volcanoes of California, and the eastern part goes under Nevada, under Salt Lake, and into Yellowstone, and then turns west under Idaho. So that plume is not directly under Yellowstone. It's coming from Baja. Now, millions of hours of computer time to create a high-resolution. That's my comment concerning the Yellowstone mantle plume from other articles that we've read, other geological articles. Now, millions of hours of computer time to create a high-resolution CT of Earth. French used very accurate numerical simulations of how seismic waves travel through the mantle and compared their predictions to the ground motion actually measured by detectors around the globe. Earlier attempts by other researchers often approximated the physics of wave propagation and focused mainly on the arrival times of only certain types of seismic waves, such as the P, or pressure waves, and S, the shear waves, which travel at different speeds. French used numerical simulations to compute all components of the seismic wave, such as their scattering and diffraction, and tweaked the model repeatedly to fit recorded data using a method similar to statistical regression. The final computation required 3 million CPU hours on NERSC's supercomputers, though parallel computing shrank this to a couple of weeks. Romanowitz hopes eventually to obtain higher resolution supercomputer images of Earth's interior, perhaps by zooming in on specific areas such as that under the Pacific Ocean or by using new data. She said tomography is the most powerful method to get this information, but in the future it will be combined with very sensitive gravity measurements from satellites and maybe electromagnetic sounding, where people do conductivity measurements of the interior of the Earth. This was by University of California at Berkeley on phys.org. Please leave your comments. Thank you for your support.